We've all seen large language models, or LLMs, do some pretty mind-blowing things, right?
Uh-huh.
Tackling incredibly complex reasoning problems, even acing advanced math competitions.
Yeah, it's truly remarkable to watch their capabilities evolve.
But what happens when the problems get really sophisticated? Requiring deep, multi-step thinking, like figuring out how to navigate a complex web of connections, a vast graph with tons of potential paths.
Right, that's exactly where the traditional approaches begin to strain a bit.
Okay.
While LLMs often use something called chain of thought or COT to show their reasoning.
Like they're writing down their work.
Exactly. It's like they're writing down each step of their thinking process, but it's typically, sequential, one step at a
Oh,
time.
whoa, okay.
So today we're taking a deep dive into a surprising new theoretical perspective on how LLMs might actually be thinking. A way that, well, it radically changes how efficiently they can solve these incredibly hard problems.
Okay, so our mission today is to really unpack this groundbreaking new paper. It offers a fundamental theoretical understanding of this approach.
Mm-hmm.
We're going to explain not just what this new method is, but crucially, why it's so powerful. I think you should get ready for some serious aha moments here.
Yeah, it really shifts how we think about AI's internal processes, for sure.
So maybe let's start with the standard way. You mentioned chain of thought.
Right. So when we talk about typical LLM reasoning, especially with that COT approach, it's fundamentally a discrete process,
Discrete meaning.
meaning the LLM generates its thought step by step using actual tokens. Think of them as individual words or, parts of words.
Got it. Like writing it out.
Exactly. It's effective for many tasks, definitely. But as you highlighted, it quickly hits a wall when problems demand deeper, more expansive reasoning or complex planning, especially over vast data sets or interconnected information.
Okay, so if that's the current state of play, this sequential token-by-token thinking, where does it really hit its limits? What kind of problem perfectly illustrates that challenge?
Well, the paper zeroes in on a specific problem to demonstrate this: directed graph reachability.
Okay, graph reachability. Break that down for us.
Yeah, so imagine you're given a network of interconnected points, like a subway map maybe, or a social media network.
Right.
You have a starting point, say your home station, and then two potential destinations. The LLM's task is simply to figure out which of those two destinations is actually reachable from your starting point, following the lines, but only in one direction.
That sounds like a classic computer science challenge.
Yeah.
But it feels like it has massive real-world implications, doesn't it?
Oh, absolutely. This isn't just some academic exercise. This kind of problem, it underlies so many real-world applications.
Like what?
Well, think about optimizing global supply chains. Can a specific raw material reach a certain factory given the current logistical routes?
Ah, I see.
Or navigating complex knowledge graphs in scientific research. Can one concept be logically connected to another through the existing literature, just knowing if one point can reach another? It's a fundamental building block for, well, countless real-world systems.
Okay, and here's where the existing bottleneck becomes critical, right?
Yeah.
For a problem like graph reachability, you said traditional LLMs.
Yeah.
How well do they do?
Well, especially those with a fixed number of internal layers, what we call constant depth transformers, using that discrete chain of thought, they can require a massive number of steps.
A massive.
The paper shows it can be O(n) squared decoding steps, where n is the number of vertices or points in the graph.
Ohm squared. Okay, for those of us not crunching big O notation daily,
Yeah.
how bad does that bottleneck actually get?
Yeah, fair point. Think of it this way. If your graph, your network, doubles in size, the traditional LLM doesn't just do double the work.
It's worse.
It does 4 times the work, potentially even more. It scales really, really badly. And that constant depth part just means they have a fixed number of processing layers, so they can't simply add more computational horsepower easily to handle the complexity.
Okay, so that makes the efficiency gap even more critical as problems get bigger.
Exactly. And this is precisely where the new approach completely changes the game.
Right. This is where the paper delivers its knockout punch. The truly mind-bending revelation, isn't it?
Absolutely. Here's where it gets really interesting. Get ready for chain of continuous thought, or coconut.
Coconut, okay.
The breakthrough here is that instead of relying on those discrete text-based tokens for internal thinking,
The step-by-step writing.
instead of that, coconut uses continuous latent thoughts.
Continuous latent thoughts. What are those?
You can think of these as hidden internal representations within the model. They don't directly correspond to words or the individual steps you might write down. They're more like internal states.
Okay, so if it's not writing down discrete steps, how is it processing information internally? This is where that superposition concept comes in, right? Which sounds almost quantum.
It is the core aha moment, and it's truly fascinating. The paper's key theoretical finding is that these continuous thought vectors behave astonishingly like superposition states in quantum mechanics.
Wow. So like in quantum physics where something can be in multiple states at once.
Kind of. Instead of being forced to pick one single path or idea at a time, like the discrete approach, these continuous thoughts can encode multiple search frontiers simultaneously.
Whoa, okay. So it's not just following one path, hitting a dead end, backtracking, trying another.
Nope.
It's exploring loads of possibilities all at once, in parallel. That really is an aha moment. How does that translate to actual speed and capability?
Well, imagine it like instead of model tracing one path, then backtracking, then tracing another. It's like running many breadth-first searches, or BFS, all at the same time inside its own internal mind.
Okay, BFS meaning exploring level by level outwards.
Exactly. Exploring all nodes one step away, then all nodes two steps away, and so on. But Coconut does this for multiple potential paths in parallel. This is in sharp contrast to discrete COTI.
Right, the step-by-step one.
Yeah, where each token generated is like a collapsed state. It's forced to choose a single path. That leads to a sequential search that takes many, many more steps and can even get stuck.
That sounds like a staggering jump in efficiency. How does this continuous thought actually manifest in such a dramatic performance improvement, like with that O(n)² problem?
It's all about that parallel processing, while discrete COTI struggles with that O(n)² scaling for graph reachability.
Meaning it gets bogged down exponentially as the graph grows.
Right. Coconut, with its continuous superposition, can solve the same problem in just D steps.
D steps, what's D?
D represents the graph's diameter. That's essentially the longest, shortest path between any two nodes in the graph.
Ah. Yeah.
And importantly, D is always less than N, the total number of nodes, usually much less.
So it can solve these problems in potentially way fewer steps, orders of magnitude faster sometimes.
Exactly. It's like finding a, well, maybe not quantum, but a computational shortcut.
So this is theoretically possible. But how does this magic actually happen inside a model? What's the underlying architecture that enables this superposition of thought? Is it super complex?
Well, what's truly astonishing is that the paper shows this incredible capability emerges from a surprisingly simple setup. Just a two-layer transformer.
Only 2 layers, that's it.
That's what they proved theoretically and showed experimentally.
Okay, let's break that down then.
Yeah.
How do these 2 layers work together to achieve this? Layer 1.
Think of the first layer as a highly efficient data organizer, maybe like a smart librarian.
Okay.
When it encounters information about an edge, a connection between 2 points in our graph,
Yeah.
its internal attention mechanism instantly identifies the start point and the end point of that connection, the source and target nodes. It then smartly copies and places that source and target information into specific buffer spaces, sort of temporary holding areas, within that edge's internal representation. It's basically getting it ready for the next crucial step.
So it's parsing and preparing the input, making sure the graph structure is represented usefully.
Exactly. Layer 1 is about getting the data in order.
Then the real magic happens in the second layer. How does that internal continuous thought start accumulating all these parallel paths?
Precisely. So the continuous thought within the model at any given step is already this dynamic representation of all the nodes it has discovered as reachable so far. It's already a superposition.
Right, that latent state you mentioned.
Yeah. The second layer's attention mechanism then allows this continuous thought to effectively look at all the incoming edges in the graph, but only those edges whose source nodes are already part of that current expanding set of reachable nodes.
Okay, so it focuses on the relevant connections.
Yes. And then, powerfully, it takes the target nodes of those relevant edges and adds them into the continuous thought for the next step. It updates the superposition.
So in one fell swoop, it's effectively expanding the set of reachable nodes in parallel, like multiple breadth-first searches happening simultaneously within that continuous state.
Exactly. It's like the model's internal thinking state is just growing, accumulating possibilities. It's this iterative parallel accumulation that allows it to achieve that BFS-like expansion so efficiently.
That's really clever. Is there anything else?
Well, there's one more piece. After that attention process, a standard component called a multi-layer perceptron, an MLP, acts as a kind of filter.
What does that do?
It basically cleans out any computational noise and normalizes the internal representations. It helps ensure that the continuous thought remains a clear, uniform representation, a clean superposition of all the currently reachable vertices.
Okay, that makes sense. And the beautiful thing about this isn't just the theory, right? It's that the researchers actually ran experiments. They proved it works in practice.
They did, and the results are pretty striking.
Tell me about them.
A mere two-layer transformer using Coconut achieved near-perfect accuracy on these graph reachability tasks. They used a data set called PROSQA.
Near perfect with just 2 layers.
Mm-hmm.
How did the standard approach compare?
Well, they contrasted that with much larger 12-layer models that relied on the traditional discrete chain of thought. Those models struggled significantly. They only reached about 75–83% accuracy.
Wow, so the much simpler Coconut model blew the bigger standard models out of the water on this task.
Pretty much. It truly highlights the immense power and efficiency of continuous thought. It's not just a little bit better, it's dramatically better, and with a far simpler architecture for this specific kind of reasoning.
And they could actually see this happening, like look inside the model's workings.
Yeah, the visualizations were really cool. They confirmed the theoretical predictions. You could see that layer 1 indeed performed that crucial data copying mechanism we talked about.
Organizing the graph info.
Exactly. And layer 2's attention consistently concentrated on edges that were reachable, and even more specifically on frontier edges.
Frontier edges?
Yeah, those edges that were exactly, say, steps away from the starting node at step I of the process. It showed it was efficiently expanding the search outward, just like that parallel BFS we discussed.
That's fascinating visual proof.
And what's maybe even more fascinating is that this entire capability, this encoding of multiple search frontiers as a superposition state, this whole parallel search thing, it emerged automatically during training.
Automatically? They didn't explicitly program it to do that.
Nope. The model wasn't explicitly told how to explore multiple paths at once or how to represent things as a superposition. It just learned it. It developed this incredibly efficient strategy all on its own as the best way to solve the task.
That's incredible. It just emerged. But okay, here's where we get to a provocative twist you mentioned earlier. Something even more surprising.
Yeah, this is pretty neat. While the theoretical construction implies a straightforward breadth-first search, like expanding evenly outwards,
Right.
the experiments revealed an additional bias in the trained models. It wasn't just exploring widely and evenly.
What was it doing?
The models allocated disproportionately more attention, more of their internal focus, to optimal edges, meaning those edges that actually led directly towards the correct solution path.
So it wasn't just doing BFS, it was doing a smart BFS.
Yeah.
Kind of zeroing in on the answer.
Exactly.
Yeah.
And also focusing more on the frontier nodes, the very edge of the current search. It's as if it developed a kind of implicit prioritization. It learned to be strategic.
Okay, but maybe that was just because of how they trained it. Maybe the training data somehow pushed it towards the right answer.
That's what they wondered, too. So to test this, they introduced an alternative training method they called Coconut BFS.
Okay, what was different about that?
In the setup, the model was trained by randomly sampling from any node on the frontier during training, not specifically guided towards the one that leads to the optimal solution, more like a pure BFS training signal.
Right, removing that potential bias. And what did that reveal? Did it get rid of this smart prioritization?
Well, what's truly fascinating is that even with this different, less biased training, the Coconut BFS model still showed similar prioritized search behavior.
No way. Even when trained randomly on the frontier, it still learned to prioritize the optimal path somehow.
Yeah. It raises a really deep and interesting question. Why does this intelligent, prioritized exploration emerge within these models, even when it's not explicitly supervised for it? It suggests a deeper, maybe almost intuitive learning mechanism at play. It hints that they're learning not just what rules to follow, but how to apply them intelligently and efficiently.
That is fascinating. So wrapping this up, what does this all mean for LLMs and, for us trying to understand them?
Well, for LLMs, I think this deep dive reveals a fundamental, highly efficient mechanism for achieving truly parallel reasoning. It's not just stringing words together.
Right.
This could potentially unlock solutions to even more complex problems that currently stump them. Problems that demand multi-step, systematic, and often simultaneous exploration of many, many possibilities. Think complex planning, scientific discovery.
And for us, for you listening. Yeah, for you understanding this concept, Coconut, Superposition. It gives you a unique insight into the absolute cutting edge of AI research.
It really shows how these abstract ideas can have real impact.
Exactly. It showcases how seemingly abstract mathematical or even physics-inspired concepts like superposition can find incredibly practical and powerful applications of machine learning. It's a profound reminder that sometimes the most revolutionary insights come from unexpected connections.
And maybe that these models are still full of surprises for us.
Definitely.
Okay, so in summary then, this deep dive has shown us that continuous thought in LLMs allows for a kind of parallel superpositional style of reasoning. hmm Making complex tasks like graph reachability vastly more efficient than the traditional discrete chain of thought approaches.
Much faster, much more scalable, potentially.
And this leaves us with a final, maybe provocative thought to chew on.
Okay.
If these continuous thoughts can automatically develop highly efficient, even prioritized search strategies without explicit guidance, what other incredibly sophisticated reasoning capabilities might be quietly emerging within these vast models that we're only just beginning to uncover?
A bit spooky, but also exciting. What else are they learning on their own?
Exactly. What else is hiding in those latent spaces?